So we move on to non-homogeneous equations. So it's the next step, next type of equations after homogeneous equations. So if we recall, an nth order homogeneous equation is some function of x multiplied by the nth derivative plus some other function multiplied by the n minus first derivative, a function multiplied by the first derivative, and some function. The right-hand side is 0. So if the right-hand side is not 0, say if it is a function, then the same equation that we have would become non-homogeneous. So the right-hand side, which was 0, made it a homogeneous equation. Now it is not 0, rather it is a non-zero function. So that is a non-homogeneous equation. How to solve? So the very first step is to treat the non-homogeneous equation as a homogeneous equation, and we've seen multiple methods to find the solution of a homogeneous equation, and we can obtain or use one of those methods to obtain a solution. So obtain the general solution. And this general solution is called the complementary solution, or complementary function. Now we go back to the original equation and we obtain another solution, which is called the particular solution. The particular solution is free of arbitrary constants. If you recall, the general solution, we have C1y1 plus C2y2 plus C3y3 and so forth. Now, when we find a particular solution, though, there will not be any arbitrary constants, C1, C2, and C3, and so forth. So the final solution would be the sum of the complementary solution that we get from the the homogeneous part, and the particular solution that we get for the non-homogeneous part. We add them together, we get the final solution. If you recall, we had a superposition principle for the general solution, which simply states a linear combination of general solutions is also a solution to a DE. So the same thing holds here if yp1, yp2, ypk are particular solutions then yp1 plus yp2 all the way up to ypk, the sum of those would be a non-homogeneous DE.
We do it every night. Every night.
Apologies. Now, here we have a family of solutions for the differential equation, and if you observe, you could see that the right-hand side here is not 0. Which would imply that the equation is non-homogeneous. We have a solution here that's given in the problem, and that solution has two parts. So the first part that you see there has arbitrary constants, so that would be the complementary function, and that part right there doesn't have any arbitrary constants, so that would be the particular solution. And we want to know if this combination of solutions is a solution to the DE. So all we have to do is take the solution and plug it in the equation to see if it satisfies the equation. So the left hand side is that. So we need to find y prime, y double prime. That's a prime, I forgot to put the derivative there. So y prime is 2c1 e raised to x plus 5c2 e raised 5x plus 6 e raised x. Y double prime is 4c1 e raised to x plus 25c2 e raised 5x plus 6 e raised x. And we just have to take these values and plug it in the equation to see if it holds true. So the left hand side is y double prime minus 7y prime plus 10y. So that would equal to 4c1 e raised to x plus 25c2 e raised 5x plus 6 e raised x minus 7 times 2c1 e raised to x, 5c2 e raised 5x plus 6 e raised x plus 10 times c1 e raised to x plus c2 e raised 5x plus 6 e raised x. Distribute, we would have 4c1 e raised to x, 25c2 e raised 5x 6 e raised x minus 14 c1 e raised 2x minus 35 c2 e raised 5x plus 10 c1 e raised 2x plus 10 c2 e raised 5x plus 60 e raised x. Combine like terms, so those will get cancelled, those would get cancelled, and I'm missing one term here. Forgot to multiply the last term, minus 42 e raised x. So that would give us 6 e raised x minus 42 e raised x. It's negative 36 e raised x. So we get 24 e raised x. And that is the non-zero right-hand side that is given in the problem. So y equals c1 e raised 2x plus c2 e raised 5x plus 6 e raised x is a solution to the given non-homogeneous D. So this is a problem similar to the previous one, only in this case we have trigonometric functions, it's just variety. So y is c1 cosine x plus c2 sine x plus x sine x plus cosine x multiplied by ln of cosine x. Again, there are two parts. That's part 1, it's part 2. That part is the complementary solution, and that part is the particular solution. Why is that the complementary solution? Because it has the arbitrary constants C1 and C2. And the other part is the particular solution because it doesn't have any arbitrary constants. So we want to plug this in the given equation and see if we have a solution. So y prime is negative c1 sine x plus c2 cosine x. I have to use product rule here. X cosine x plus sine x times the derivative of x is 1. Product rule again. Cosine x. Derivative of ln of cosine x is 1 over cosine x multiplied by the derivative of cosine x is negative sine x. That is the chain rule. We still have one part left, ln of cosine x multiplied by the derivative of cosine x, which is negative sine x. Simplify before proceeding. So we have negative c1 sine x plus c2 cosine x plus x cosine x. Those two terms will get cancelled, so we have negative sine x multiplied by ln of cosine x. Now we find the second derivative, negative c1 cosine x, negative c2 sine x, product rule again, x times negative sine x plus cosine x times 1 minus sine x multiplied by the derivative of ln of cosine x, 1 over cosine x multiplied by its derivative, which is negative sine x, plus ln of cosine x multiplied by the derivative of sine x with the negative, we have negative cosine x. So we have minus c1 cosine x minus c2 sine x minus x sine x plus cosine x plus sine squared x over cosine x minus ln of cosine x multiplied by cosine x. We take that and plug it in the original equation. Now consider that is the left hand side, y double prime plus y. And y double prime plus y is negative c1 cosine x, negative c2 sine x, negative x sine x plus cosine x plus sine squared x by cosine x minus ln of cosine x times cosine x, and add y to it. Y is c1 cosine x, c2 sine x, x sine x, and ln cosine x times cosine x. So those would get cancelled, and you end up getting cosine x plus sine squared x divided by cosine x. You look at that and you may immediately jump to the conclusion and say, oh, that is nowhere close to the secant x given in the problem, so the given solution couldn't be a family of solutions for the differential equation. That is not true. This is where you've got to think of trigonometric identities a bit. So y double prime plus y, it would equal to this term right here. I'm going to get a common denominator, so cosine x multiplied by cosine x divided by cosine x plus sine squared x divided by cosine x. Y double prime plus y would equal cosine squared x over cosine x plus sine squared x divided by cosine x. We have a common denominator. And if I add those two, we have 1 over cosine x. The trigonometric identity is sine squared x plus cosine squared x is 1. So that would just reduce to secant x. So 1 over cosine x is secant x. So the given solution is in fact a family of solutions for the differential equation. So we have y1 is equal to 3 e raised to x, y2 equals x squared plus 3 raised x. Our particular solutions to the DE. Why is this a particular solution? If you look at it carefully, they do not have any arbitrary constants. You simply have numbers and x's and functions of x's. So no constants, so they are particular solutions. So the first DE that we have is y double prime minus 6y prime plus 5y equals negative 9 e raised to x. And the particular solution corresponding to that DE is 3 e raised to x. If we have a general solution, the general solution would satisfy the DE. It would satisfy the homogeneous DE. It would satisfy the non-homogeneous DE. So by satisfying the non-homogeneous DE, I mean if we set it equal to 0 and plug in only the general solution part, it will satisfy that non-homogeneous DE. So, and the particular solution will satisfy the non-homogeneous DE in its entirety. So, in other words, when I take this y1 and plug it in this DE, I must get negative 9 e raised to x. So what is y1 prime? y1 prime is 6 e raised to x. y2 prime, y1 double prime is 12 e raised to x. Got to plug that in. We get 12 e raised to x minus 6 times 6 e raised to x plus 5 times 3 e raised to x. You get 12 e raised to x minus 36 e raised to x plus 15 e raised to x. 27 e raised to x minus 36 e raised to x. We get negative 9 e raised to x. So it matches the right hand side. So y1 equals e raised to x times 3 is a particular solution to the given DE, which is y double prime minus 6y prime plus 5y equals negative 9 e raised to x. The second equation has a solution x squared plus 3x, and the equation is y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16. So I have to plug in y2 prime, y2 and y2 double prime to see if I get the right hand side, the non-homogeneous part, which is 5x squared plus 3x minus 16. So y2 double prime can be found using y2 prime first. So 2x plus 3, and y2 double prime is simply 2. So y double prime minus 6y prime, let me write it here, plug in y2 prime, or y2 prime, and y2 double prime in the DE, the left hand side. This would imply y double prime minus 6y prime plus 5y. That would equal to 2 minus 6 times 2x plus 3 plus 5 times the given y2, which is x squared plus 3x. Combine like terms, we have 5x squared plus 3x minus 16. So x squared plus 3x is a particular solution for y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16. So here we have an interesting problem where we have y double prime minus 6y prime plus 5y equals negative 9 e raised to x plus 5x squared plus 3x minus 16. And the other DE is y double prime minus 6y prime plus 5y equals minus 10x squared minus 6x plus 32 plus e raised to x. And we have to make use of the results from the previous problem. And the goal here is to find a particular solution. The key thing to understand here is superposition principle. I didn't write a generic case here when I wrote the principle. I'm going to throw in constants. Even though that is a correct answer, we need to have constants here, k1, k2. Oh, bad choice. And you may say, oh, there are constants there, so why would you call it a particular solution? A particular solution shouldn't have constants. So the values of C1, C2, all the way up to CK are fixed real numbers. So if we have particular solutions, a linear combination of particular solutions is also a particular solution. We're going to use that idea here. So let's start from the right-hand side. For the first DE. And you can see that the right-hand side is a linear combination of the solutions, of the right-hand sides of the previous two equations. So we had negative 9 e raised to x, 5x squared plus 3x minus 16, added those two, and I ended up getting that. So that tells us yp equals 3 e raised to x, which is a particular solution for the first equation, which is right here. And x squared plus 3x is the particular solution for the second equation, which is y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16. So since I'm adding the right-hand sides here, my guess is the solution is 3 e raised to x plus x squared plus 3x particular solution to the DE. Why? I'm simply adding the right-hand side, so the non-homogeneous equation with that right-hand side has a solution 3 e raised to x. The non-homogeneous equation with that right-hand side has a particular solution from the previous problem. So the particular solution is simply the linear combination of those two. Great. I am pretty confident about this, but it's good to verify. So we need to plug in yp prime, and yp double prime in the left-hand side, and it should satisfy the equation. and they must let us see if that happens. So in order to do that, we need to find yp prime, which is 6e raised to x plus 2x plus 3. Yp double prime is 12e raised to x plus 2. Plug those in. Yp double prime minus 6y prime plus 5y equals 6e raised to x plus 2x plus 3 minus 6 times, 12e raised to x plus 2 times 6 plus 2 times 6e raised to x plus 2x plus 3 plus 5 times y, that is my particular solution, or yp, three e raised to x plus x squared plus 3x. So we have 72 e raised to x plus 12 plus 12 e raised to x I don't know why I put 2 there. That should be a negative 6. Negative 12x, negative 18, plus 15 e raised to x, plus 5x squared, plus 15x. Okay, let's combine like terms. I don't understand why I have a 6 here. Shouldn't be there. Knew I was doing something wrong. So that should simply be 12 e raised to x plus 2. Combine like terms. When I combine those, I would end up getting minus 9 e raised to x. When I combine the x terms, I would get 3x. When I combine the numbers, I'd have 2 minus 18, which is minus 16. And that matches up with what's given in the problem, the right-hand side. So yp equals 3 e raised to x plus x squared plus 3x is a solution to the DE, non-homogeneous DE, So the second equation that we have, things aren't quite obvious here. So y double prime minus 6y prime plus 5y, that is the right-hand side. That's the left-hand side. The right-hand side is e raised to x minus 10x squared minus 6x plus 32. And that is what we have. Now, what I'm going to do is I am going to rewrite this term so that it matches up with the right hand sides of the previous equations that we had, which is 9e raised 2x with a negative in the front and 5x squared plus 3x minus 16. Is it feasible? So let's see. Multiply and divide by negative 9. And I am going to pull a negative 2 out. I have 5x squared plus 3x minus 16. So which would simply mean negative 9 multiplied by negative 9 e raised 2x. That is the first, negative 1 over 9. That is the first right-hand side of the previous equation. Or equation in the previous problem. And this is the second right-hand side, which is negative 2 plus 5x squared minus 16. And if you recall, I talked about the constants C1 and C2 in the particular solution. That would be C1 and that would be C2. And this is what I meant by those are fixed real numbers. They are not arbitrary constants because a particular solution cannot have arbitrary constants. So my thoughts now is that right-hand side is a linear combination of negative 1/9 of that term, negative 2 of that term. We know the equation with negative 9 e raised to x has a solution 3 e raised to x from the previous problem. We know the differential equation with the right-hand side of 5x squared plus 3x minus 16 has a solution of x squared plus 3x from the previous problem. So since I've combined the right-hand sides in this manner, negative 1/9 of the first right-hand side plus negative 2 of the second right-hand side, my claim is the particular solution is yp equal to negative 2 times the solution to the right-hand side 5x squared plus 3x minus 16, negative 1/9 multiplied by the solution for the right-hand side negative 9 e raised to x, which is 3 e raised to x. So that would give me negative 2 x squared, negative 6x, negative 1 over 3 e raised to x as a solution to the equation that we have. Let's verify, so check. So plug in yp prime, yp double prime, yp prime, and yp in yp double prime minus 6y prime plus 5y the second equation. So right here, and we must get that right-hand side. I'm saying if the non-homogeneous part is a linear combination of the previous two non-homogeneous parts of the equation on the left-hand side, which is y double prime minus 6y prime plus 5y, and what I have here must be a particular solution. So I'm going to plug those in and see if it works out. Yp prime is minus 4x minus 6 minus 2 over 3 e raised to x. Yp double prime is negative 4 over 3 e raised to x. Plug those in, negative 4 over 3 e raised to x, negative 6 times negative 4x, negative 6, negative 2 over 3 e raised to x, plus 5, the solution that I am claiming to be the solution, which is this particular solution. So 5 times negative 2x squared, negative 6x, negative 1 over 3 e raised to x. Distribute and simplify. Minus 4 over 3 e raised to x, plus 24x, plus 36, plus 4 e raised to x, minus 10x squared, minus 30x, minus 5 over 3 e raised to x. Let's start adding things up. The e raised x terms, if I combine that term and that term, we have 36 minus 4 is 32. Combine those two, I have negative 9 over 3 e raised to x. Plus the x terms, 24x minus 30x would be negative 6x. And plus 4 e raised to x minus 10x squared. Well, 9 over 3 is 3, so negative 3 e raised to x plus 4 e raised to x is simply e raised to x. And the rest would be negative x squared, negative 6x plus 32. And that matches up with the right-hand side here. So the idea is to show that if we have non-homogeneous DEs, and we have particular solutions for specific right-hand sides, such as these, then I could come up with a new DE with the left-hand sides being, the same as in the previous two right-hand side equations. And you take any linear combination of the right-hand sides, and you can manipulate the particular solutions, and the corresponding linear combination of those particular solutions will also be a solution to the DE. So here I simply added the two right-hand sides to get that part. So the solution is the linear combination, direct linear combination of the two particular solutions from the previous problem. The right-hand side here is a specific type of linear combination. I take negative 1/9 of the first solution and negative 2 of the second solution, because we have negative 1/9 of the first right-hand side part, negative 2 times the second right-hand side part. So I combine the solutions with the same proportion, and I end up getting this to be the solution. So just by looking at a particular solution, we should be able to come up with new particular solutions for non-homogeneous DEs. So the key to solving a non-homogeneous DE is to start with the homogeneous part of the DE, get its complementary function, then find the particular solution, add them together, you get the solution to the non-homogeneous DE.